Okay, so we are going to continue our discussion about Newton-Raphson's algorithm. And recall, just to set things up, in the previous video we discussed that we have the objective function being f theta, and we want to find the argument that maximizes f of theta. Sorry, we want to find the argument that maximizes f of theta, and that is our theta star. So our whole goal is to find this theta star. And the way Newton-Raphson's algorithm works is it takes our function of interest. At a current point theta k, it draws a quadratic curve or a quadratic approximation using Taylor series, and then finds the maximum or maximizer, the optimizer rather, optimum of this quadratic approximation. Okay, and then just keeps doing that at every successive step in the hopes of converging to the optimum. Okay. Now, we also discussed that although this is great and it actually worked really well for the gamma example, gamma maximum likelihood function, let's take a look at a location Cauchy example. So consider the following data where we have a location Cauchy distribution with mode at mu at a value mu. That's a real value, mu in R. Okay. Now the goal is to find the maximum likelihood estimator for mu. Having observed the data x1 up to xn, IID from this Cauchy with mode parameter mu. Okay, so this is basically, if you haven't seen this before, you have a Cauchy distribution, a sort of Cauchy which is basically a t, which is typically centered at 0. But now this location Cauchy is basically this, which is typically now centered at some unknown value of the mean mu. Not the mean, sorry, the median or the mode mu. Okay. Now, the density of such a distribution, a location Cauchy can be written as f of x given mu. So I'm going to use given mu as an idea that given the true mode mu, this is going to be the density. So it's 1 by pi, 1 by 1 plus x minus mu squared. So we're basically taking our density function and displacing it by shifting it by a unit, by mu units. Now this is our density function. So what we can do is find the maximum likelihood estimator, to find the MLE for mu. What I need is to set up the likelihood function mu given x, which is nothing but the product I going from 1 to n of f of xi given mu. Right? And this product over here is as a consequence of the fact that my data are independently obtained. Right? And so this is the way we set up our likelihood. So our likelihood mu given x is this thing over here, which means I can just take this PDF and product it everywhere for the given data point xi's. Now I can take the log of this likelihood, because typically, as we've discussed, taking the log is going to be easier to optimize. So L of mu is log of, small l of mu is log of L, which is then minus n log pi, where pi is just the number pi, minus the product becomes summation. So summation t going from 1 to n, log of 1 plus xi minus mu squared, which now this whole objective function I denote by f mu. Now I will grant that there is little confusion of notation. Typically f is used for density functions as well, and f is also often used for objective functions. And so I'm going to basically use them interchangeably. It should be clear from context what f is. Now, in order to do this, in order to find the maximum likelihood estimate, I need to find the first derivative, set it to 0, and hope that there is a closed form solution. Now, when I do that, when I take the first derivative with respect to mu over here, this is constant, so this goes away. And over here, this is a sum, so I get, and there's a minus over here that will cancel with the minus here, so I get positive 2 times summation I going from 1 to n. And then the 2 comes over here, so I have x minus mu divided by 1 plus xi minus mu squared. Right? So that's simple. But if I set it to 0, you see that because of the summation here, I can't really isolate the mu in order to solve this problem, to actually obtain mu. So mu at MLE is not available in closed form, right? And hopefully that's not surprising to see. Now I've already taken the first derivative. I know that when I don't have MLEs available in closed form, I could use Newton-Raphson. So in order to implement Newton-Raphson, I need the second derivative, which is what I get over here. So now I can do this, by parts or by the chain rule for ratios. So I get 2 on the outside, summation on the outside, and then another 2 x minus mu squared by 1 plus this, minus 1 because of this divided by 1 plus x minus mu squared. Okay, well, this is interesting because you see that this term is positive, this term is positive, or this term is completely positive, minus some term over here. Okay, now it is possible for certain values of xi and mu for this expression to be either greater than or less than the first expression. What I'm trying to say is that this whole thing can either be positive everywhere or can be negative everywhere, or it can be positive and negative in different parts. But the key idea is that it's a function of xi. Okay, so the sign of f double prime mu depends on the data observed. Okay. Now notice this was not a feature we saw in the gamma likelihood. The gamma likelihood's objective function, when you take the second derivative, was always concave everywhere, which means the second derivative was always negative. No matter what data you saw, you would see the second derivative to be always negative everywhere in the parameter space. In this setup, the second derivative can change its sign based on the data observed, and where it changes the sign can also be different based on the value of mu and the data observed. Okay. The key thing being that this then function is not generally going to be a concave function, and this implies, given our discussions previously, that Newton-Raphson is not guaranteed to converge to a global maxima. In fact, it may not even converge to a local maxima, and it may converge to, in fact, also a local minima. So it could converge to a global maxima or a local maxima. It could diverge altogether in that it just keeps going and doesn't never converge. Or it might also converge to a local minima, which is the complete opposite of what we want. Which means we need to be careful in choosing our starting values for our setup. So for this, the way to actually implement the algorithm would be you set a mu0, right? Which is, we need a good starting value of mu. Now we know mu is our mode of the distribution, but we also know it's the median because it's a symmetric density. So we can start from the sample median of the data that we have observed, not the mean, because the mean of the Cauchy does not exist. So the sample mean is likely going to be an unstable value. And so we don't want to use the sample mean, we want to use the sample median. Now, once we have that starting value and we have a tolerance, we determine the next mu by mu k plus 1 is equal to mu k minus f prime. And we stop when, now I'll just fix this a little bit. We stop when the update size of the mu's is small, smaller than some tolerance, or, and this is what we end up using, if f prime mu k plus 1 or mu k is less than epsilon. Okay. So if the first derivative is close to 0, we know that we've come sufficiently close to where we want to be because we know we've reached an optima, and so we can stop getting our sequence. Okay. Now, then the Newton-Raphson algorithm proceeds as we would have proceeded. So what I'll do is I'll just show what happens. I'm not going to show the code because we're going to switch to R soon where I'll run the code for you. But let's just look at the output of the code. is this is exactly what we see when we run our Newton-Raphson iteration. So this is the output from Newton-Raphson. And I'll show the code right after in maybe 2 minutes. What I do is I start from three different starting values. I start from a good value, a bad value, and a horrible value. The good value over here is the median, the sample median as discussed. That is a good value. And when I start from the sample median, turns out the sample median is fairly close to where the maxima actually occurs. And so I get convergence to the global maximum. Okay, I should say that I'm plotting the log likelihood over here. But if I start from a bad starting value, which is this, where what's happening over here is you note that over here we have a decreasing function, which means f mu k is less than 0. But also we have a function that is actually convex, which means f double prime over here is positive. Now, when I look at their ratio and take a negative over here and put a theta k, sorry, not theta, it's mu k, I see that there are two negatives, which means it's a positive. So I'm adding a positive value to this, which means I go from this direction to this direction, which is exactly where I land up here. Okay, and this is primarily because I have convexity in this part. If I had concavity, then I would go in the opposite direction. But I have convexity, so it goes like this. And which means it goes from here, and over here it sees the same thing, so it goes here. Over here it sees the same thing, so it goes here, and finally it converges here, which is in fact the wrong place to go because it's a local minima, not a local maxima. So not the actual optimizer that we want. An even further horrible starting point is starting from here, where with the same logic, because this is the derivative is negative, the second derivative again is negative, is positive, and so now from here it sort of keeps going here, 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 and the sequence is just going to diverge. It's never actually going to converge because there are no more optimas happening in this direction. Okay, so the starting value when our objective function is not concave becomes highly, highly important. So let's actually look at the code. I sort of skipped the code when I presented this because we're going to look at the code more in R right after this.